I just want to quickly go over this minus 20 dB slope per decade thing when we come to the frequency response of a single time constant circuit. So remember, the slope here is falling off at minus 20 dB per decade. That's a decade change in frequency. And what we really mean is a plot like this. If this was a low pass circuit, just looking at low pass, but the same goes for the high pass and basically the whole amplifier response. We could have a midband gain, a gain at the midband, and from that, if we subtract 3 dB, we would have some gain, and that actually is AM minus 3 dB. If the midband gain was 150, then you would have a gain at that point of 150 minus 3 is 147. And if we find the frequency that occurs, that would be the minus 3 dB frequency. It sometimes gets called other things, but anyway, I would often call it the minus 3 dB frequency. And another important place is the 0 dB frequency. And that would be the place where the gain falls to 0 dB. And it also has some other names. Now remember, gain is 20 log of output over input. In dB. And that's really absolute value. And of course, 20 log of the place where output equals input. So we have V out, or let's call it Vn, over Vn, that is equal to 20 log of 1, that equals 0. That's what we mean by 0 dB. 0 dB gain would just be a gain of where the output equals the input. And that frequency is very important. If we know two of these points, and you kind of pick whatever points, if we know this point and we know this point, if we know the f minus 3 dB frequency and know the 0 dB frequency, for instance, and we know the slope of this line along here is minus 20 dB per decade, then we can work out some things. For instance, we can work out what the midband gain is, because we just kind of work our way backwards. But you've got to keep in mind that we're talking about per decade. So what does that mean? If you turn your head sideways, I've got the scale here, and it's well, we're taking log f would be the real numbers I've drawn, but it's a logarithmic scale. So for instance, we've got 0.1 hertz, and then 0.01 hertz, then 0.1 hertz, and 1 hertz, and 10 hertz, and 100 hertz, 1 kilohertz, 10 kilohertz, 100 kilohertz, 1 megahertz, 10 megahertz, 100 megahertz, 1 gigahertz, like that. The whole way, I'm just talking an increase of 10 in the frequency. That's what we mean by a decade change in frequency. And if we happen to know that f0 dB is equal to 10 megahertz, and if we in fact have a single time constant circuit like this, let's see if I can make that a little room there. if f0dB is equal to 10 megahertz, and f minus 3 dB, for instance, is equal to 10 kilohertz, like I've shown here, we can work out what AM is. So at, and one way you can just do it is you can just make a little table. So frequency and gain we'll start at the 0 dB frequency, 10 megahertz. Our gain is 0. And if we change a decade in frequency, so right now we're going, if we decrease, we go that way, that means we're working up. So it's minus 20 dB going down, it's plus 20 dB going up per decade. So at 1 megahertz, that's a 10x change, we would be at 20 dB. And at 100 kilohertz, we would be at 40 dB. And so at the minus 3 dB frequency at 10 kilohertz, we would be at 60 dB. So that must mean that AM is 60 plus 3 is 63 dB. It's that simple. You don't need to make it crazy hard. I'll make a little simple example so you can practice some, just so you can make sure you get this. But it's not crazy hard. People get really confused by it. We can also use the line of an equation, y equals mx plus b. We've got the slope. And we've got x, that's the log f. And we've got y, that's the gain. And we have an intercept, the y-intercept. You can figure these things out. That would be the equation for a line, but you don't need to be so fancy. You can work out a table like this, and you can understand these things. And so I could give you the midband gain and the 0 dB frequency, and you could find the minus 3 dB frequency, for instance. There's a bunch of stuff that you could work out if you know it's a single time constant circuit.